if we want to study and figure out what the size of the frictional force is, then we're going to have to analyze the forces, or if you don't want to do it that way, you could find the acceleration and then use a motion equation to work backwards. And you could find the length along the ramp and then work backwards to get the acceleration, and from there find the frictional force. But I think just finding forces is the way to go. So I want to analyze the force question. And I don't think it makes any difference whether the object is at rest or moving up the ramp or down the ramp. Just like anything else that has a problem like this, the forces aren't going to be different, whether it's rolling up the ramp or down the ramp. We've handled that. And I think the only things that I think would probably end up being at issue would be the angle. I think the angle is going to make a difference. I think it'd be easier for something to slip if the angle were very steep. Can you imagine that? Rolling something up a very steep wall or a very steep surface, I think it would be more difficult to stay rolling. And I think, obviously, a flat surface, it would be easier. So I bet the angle plays a role in this. And I think, I don't know if the mass is going to play a role or not, but I'm sure the shape is going to play a role. I think the shape is definitely going to play a role. But what I would like is I want the size of the frictional force, like an expression for it. Now, the mass will make a difference. We know this because the mass is going to control how hard the object is pressing into our surface. And we know that friction is based on the normal force. However, friction is an inequality. I don't know that this expression is going to help us, because the size of the frictional force is probably very small compared with the threshold of the frictional force. So I don't know that that's going to be useful. We could maybe make that useful if we want to figure out something about the threshold, the smallest amount of coefficient of friction that would still allow for something to roll or something like that. That might show up. So if you don't know where to begin, that makes me sad, because you should know where to begin, because we did forces for the entire first semester. So you should be able to start this problem out and look at the forces acting in the system without any issue at all. Something about maybe drawing a free body diagram, and then from there taking a coordinate system and applying it on top of this problem. And then from there, breaking up any off-axis forces into their components. You know where I'm going with this, right? Something that we're supposed to be experts in because we've done it way many times. So why don't you start that part? Get ahead of me. And then I will suck some tea, and then I will join in with you guys. So I see 3 forces. Is that what you see? I don't know if they're well drawn to scale, but mg, normal force, friction. Doesn't matter whether this object's going up the ramp or down the ramp, that's going to be the direction of these forces. I'm going to need to establish a coordinate system that can be used to help me take the forces and break them up into their components, and I'm going to choose a coordinate system that's aligned with the direction of the acceleration, which is down the ramp. In fact, I'm going to make down the ramp the positive direction for this problem. And that's going to mean that into the ramp is going to be the negative direction in the y, and perpendicular to the ramp will be the positive direction in the y. I'm going to have to take my weight and break it up into 2 components. I think that's pretty easy to understand. So I'll have a component of the weight this direction, mg sine theta. And I have a similar component into the ramp, like that I will call mg cosine theta. And there we go. I believe the object has an acceleration this way, whether it's going up or down the ramp, right? And an angular acceleration this way, whether it's going up or down the ramp. All good? All righty. So let's start with net force in the x direction equals ma. So mg sine theta minus friction equals ma. I'm very confident that mg sine theta is going to be greater than the frictional force because the acceleration is down the ramp. In all circumstances, that's going to be true unless the object starts to slip. At the same time, net force in the y direction equals 0, so normal equals mg cosine theta. Now we want to solve this for the frictional force, but we don't know the acceleration. So although things like mg theta likely to be allowed in our answer, A, not so much. Now this is where you could use conservation of energy and kinematics to come up with an expression for the acceleration and sub it in here. But we've left something out that we could use here, correct? We haven't talked about the torque yet. Seems to me that we could talk about the torque. I think there's an unbalanced torque acting in our system. Would you agree? Now, to deal with the unbalanced torque, we're going to have to deal with the idea that we could choose a pivot point that might make us think we should eliminate friction between our equations. We don't want to do that. I mean, if we do that, we can't solve for friction if it's been eliminated between our relationships. If we want to solve for friction, we would like to eliminate acceleration between our relationships. That should leave us with something that has friction equals. You follow what I'm saying? Now you could eliminate friction, solve for the acceleration, and then go back and figure out what the frictional force is. That would work just fine. But I think we should just solve for the frictional force. Now, you have a couple of opportunities for how you might want to do this. We could put the pivot point at the center of the round object. That would be fine. Or we put the pivot point at the point where the object touches the surface. That would be fine. It actually pivots about that point. But I'll let you guys choose. What direction would you guys like to put the pivot point? Would you like to put it at the edge? Or would you like to put it at the center? Okay. We can do center. There's positives and negatives to doing it that way. But let's just do that. Put it at the center. I'll put the pivot at the center. There we go. I see one frictional torque that's going to act to cause the object to have a counterclockwise acceleration, or an acceleration that is out of the board. Would you guys agree with that statement? In order to be consistent, that's got to be a positive direction. Any question about that? Okay. Then that means net torque equals I alpha. I never said what round shape this was, so my intention is to leave this in terms of I. That way we've solved it for every round object. And then at the end of this, you could just put in mr squared, or 1/2 mr squared, or 2/5 mr squared. Is that okay with all of you? I never said it was a disk. You guys try to put words in my mouth about what kind of round object. I just said it was round. Everybody good? Alrighty. I'll remind you that torque is r dot f dot the sine of the angle between them. There's a couple ways we could do this, but I do want to point out, and this is hard to see, but this is the force that's causing a torque, right? Now, we put the pivot point there, so this is the force we're going to be using that's causing the torque. You follow what I'm saying? But the truth is, it pivots about this point right there. So I'm only bringing it up because we have mg and the angle, so we would have been able to build a torque just fine. We just would have shifted our moment of inertia. But we're going to go with this. The problem with this is that means my torque arm, of course, is the radius of the object. My force is friction. And the angle is going to be sine of 90 degrees. based on friction's relationship with the radius. That all good for you guys? Alrighty. So RF sine 90 equals I, and I'm going to go ahead and make a substitution, A over R. Any questions about why I made that decision? Okie dokie. Now I don't want to solve this for F. I want to solve this for A. So that's what I'm going to do. Now, I guess you could say we could solve this for F right now, but it has A in it. I don't want that. I want to eliminate A. So I'm going to solve this for A and sub it in over here. So a little bit out of space. We'll do it right here. A equals F R squared over I. Any questions about what I did there? Alrighty. So now I'm just going to go ahead and grab this because we're going to use it. Mg sine theta minus F equals Ma. I want to solve this for F. Okay, everybody? So I'm going to move F to the other side. I'm going to regroup this, and I think you'll understand why I'm going to regroup it the way I am. Does that make reasonable sense? So I'm going to factor out an F. Divide by that term. Alrighty. That's the frictional force in terms of all the other things. Some things here make sense to me. Some things here don't. It's going to take a lot of friction if I want to make that angle steep, isn't it? A lot of friction. Our friction goes up, meaning I need more friction if I make the angle bigger. Do you guys all see that okay? At the same time, let's look at the bottom of this. I see some stuff in the bottom that may or may not make sense to you. Do we understand that this is just going to be a fraction? Or a number, right? Maybe not a fraction, but so like if it's a ring, that number's 1. If it's a disc, that number's 2. You guys all see that okay? That means the friction gets smaller if it's a disc than if it's a ring. Does that agree with our thoughts about this? I think it does. I think it agrees very much with our thoughts about this. There is something I'd like you to consider. This is the frictional force. It has to be less than or equal to mu times the normal force. Now, this looks way crazy. Like, what are you getting at, Mr. Shelton? Getting at a lot of things. This is the threshold. Right? It tells you threshold information, like what can the max angle be under certain circumstances. If I solve this for mu, it would tell me how sticky my surface would have to be if I want something to be able to roll up or down a ramp without it breaking friction. Right? It'd be hard to solve this for theta, I think. You can probably see why that's true, but I think it's not impossible. It'll just give us a tangent somewhere in there, right? You know, sine over cosine. I think that's probably the way we'd go. M cancels out under this circumstance, as does G, because we're now no longer comparing those same things. But if you were asked like whether a disk or a ring would be able to roll under some circumstance, this would tell you, wouldn't it? All right.